Why did two binary crystals, like sodium chloride and cesium chloride, behave so entirely differently, even though they look practically identical on paper? But actually, here's a much more important question. Which of your three possible revision strategies is actually going to earn you those top marks when you have to explain that difference in your 9702 physics exam? I mean, are you just endlessly rereading the textbook? Are you grinding through past papers without a real game plan? Or do you have the specific, analytical framework that the examiner is desperately looking for? Look, if you're just relying on passive reading and repetition, you're literally risking a ton of easily avoidable dropped marks. Let's fix that right now. So picture three doors in front of you. Behind doors 1 and 2, well, that's your standard revision technique, just generic textbook label memorization. But behind the third door, that's where the magic is. That's the hidden pattern. It's the specific examiner logic that's going to prevent you from bleeding marks and completely buckling under that crazy exam timing pressure. Today, we're opening that third door and uncovering exactly how to correctly analyze these physical structures.
Section 1. Decoding binary crystal structures and the mistakes you absolutely have to avoid. Okay, let's dive into this, because when we look at solid-state physics, there is this massive, painful pitfall that almost every single learner makes.
You have got to stop memorizing labels without the physical explanations. Seriously, stop your ordinary revision habits right now. Memorizing names of structures is a total trap. In those extended exam questions, examiners are hunting for the underlying physics driving the macroscopic phenomenon. They don't want just a scattered collection of facts. Trust me, scattered facts will shatter your grade boundaries. If you simply write down face-centered cubic without explaining what that actually means for the atomic interactions, no way are you getting the marks you deserve.
Let's define binary crystal structures with absolute precision. We are interpreting the macroscopic behavior of a solid based strictly on its internal atomic or carrier level arrangements. A binary crystal, it's simply a crystal lattice composed of two different elements, like sodium and chlorine in NaCl. And this is absolutely crucial because that internal crystal arrangement controls literally everything on the outside. It controls the packing density, the bonding direction, the defect tolerance. For instance, sodium chloride forms a face-centered cubic lattice where each sodium ion is surrounded by 6 chloride ions. But cesium chloride, it forms a simple cubic structure, so each cesium ion is surrounded by 8 chloride ions. That tiny difference in coordination number, just 6 versus 8, completely dictates the material's tolerance to physical defects. It's a real game changer.
Section 2. The 4-step cause and effect framework. Let's switch tactics here. I'm going to give you the ultimate quick win for your Cambridge exams.
Now, what's really interesting about this slide is the rigid 4-step structure that examiners are basically begging to see. It's the ultimate safe framework for short and extended questions. Step 1, define the idea. For example, explicitly stating we have a binary ionic lattice. Step 2, describe the microscopic mechanism. This is where you bring in the heavy hitters, like the ratio of ionic radii dictating whether the atoms pack tightly into a coordination number of 6 or 8. Step 3, identify the measurable consequence. How does that specific packing affect the bond strength or maybe the melting point? And finally, step 4, connect that consequence to a specific application or macroscopic observation. If you walk through these 4 stages in order, you've mastered the topic. You've got to shift your mindset from just memorizing to truly understanding. You need to work backward from a visible phenomenon to the microscopic picture. Ask yourself, what physical effect happens internally at the atomic level, and why does that matter outside in the real world? Take sodium chloride again. Internally, the relatively large difference in the ionic radii of sodium and chlorine forces them into a really specific geometric arrangement. Why? To maximize electrostatic attraction and minimize repulsion. And why does that matter outside? Well, it makes the whole crystal highly brittle, meaning it cleaves along very specific geometric planes when struck. It's like a giant puzzle, perfectly locking together.
Let's anchor this theory into reality with some rapid-fire links, because real materials behave differently based exactly on these structures. Semiconductor wafers? Their specific binary crystal structure, like gallium arsenide, dictates the band gap, controlling how easily electrons jump to the conduction band. That's what makes the chip in your phone work. Turbine blades, structural alloys? The way different-sized atoms interrupt the slip planes in a metallic lattice prevents layers from sliding past each other, giving aerospace alloys immense strength. Even gemstones rely on this. Linking the microscopic physics to these real-world systems in electronics and energy makes the theory so much more memorable.
Section 3. Spot the fatal error. We're escalating the stakes now with a pressure test.
We're going to break down a typical student response, and I want you to spot exactly where it all falls apart. In a moment, I'll show you the examiner clue that changes the answer completely. But first, you need the framework that makes that clue obvious. Think of this as handing over a secret weapon. Here is the ultimate top-band framework. Step 1. State the concept. Step 2. Provide the evidence or data, like that specific ionic radii ratio we talked about. Step 3. Apply the scientific reasoning. That means explaining the internal atomic mechanism detailing those electrostatic forces. And Step 4. Lock it all in with precise examiner wording. This is exactly how you turn a theoretical scattered understanding into a flawlessly structured exam paragraph.
Section 4. The perfect exam answer and the examiner correction. We're going to play examiner right now and correct those fatal errors side by side.
And this brilliantly illustrates exactly where you bleed marks if you aren't careful. A flawed answer simply states an application. It might say, gallium arsenide is used in semiconductors because it has a binary crystal structure. Okay, but there's zero microscopic link there. It just bleeds marks. An improved top-band answer links that application directly to the atomic mechanism. It reads, the difference in atomic radii in the gallium arsenide lattice determines the precise lattice spacing. This atomic arrangement dictates the specific energy band gap, which ultimately controls the semiconductor's electrical conductivity at room temperature. Boom, cause and effect. This whole idea is cemented perfectly by this golden rule, straight from the examiner's perspective. A disciplined paragraph that connects cause and effect usually scores more strongly than a scattered collection of facts. Let that sink in for a second. Do not just drop technical vocabulary onto the page hoping it sticks. You have to walk the examiner step by step through the physics.
Section 5. Your mandatory next step and dealing with the unresolved problem. Look, mastering this cause and effect theory is incredible, but it leaves a massive unresolved gap if you don't master the linked practical skills to back it up.
This brings us to the linked practical data analysis. Let me be clear. This is not an optional extra. It's an absolute mandatory pressure test. We have to map this theory directly onto your practical data analysis skills. Whether you're identifying lattice constants from X-ray diffraction data or calculating theoretical densities based on atomic mass and unit cell volume, the math is completely driven by the exact binary crystal geometry we've just been talking about.
Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. To truly dominate your exams, you've got to synthesize these concepts. Whenever you face a question about a material's physical properties, immediately visualize its internal binary lattice. Picture the atoms, the coordination numbers, the bonding forces. That visualization is your key. So, I want to leave you with this final intense challenge. Can you answer these 4 memory triggers aloud right now? What is it? What changes inside the solid at the atomic level? What is observed outside as a macroscopic consequence? And where does it matter in real-world technology? If you can't answer them all confidently right this second, you know exactly what concepts you need to revisit. Go test your knowledge, rebuild it stronger, and never settle for just memorizing the label.